Okay, what we're actually looking at, and I apologize for the lack of words, what we're looking at in this case is the malonate ester. Okay, so we're using a malonate ester for this reaction. It's a good thing it's written where you can't see it. And in that process, we went through and took our malonate ester and we reacted it with ethoxide. You'll notice I've given you two reactions with ethoxide. Tricky, in a nice big giant box. Ta-da! So if we hit next, what happens? Oh, we can see the answer. Come back. So, one of those cases, our ethoxide is acting as a base, and in the other case, it's acting as? Why would it act as a base or a nucleophile? It's negatively charged, which by definition means it has a lone pair, and or attack a carbon. Why can it do both? For instance, I could have given you this guy. Or this guy. Has to do with sterics. Ethoxide is not bulky, which means it can act as a nucleophile. Both are options for it. So guess what you get to do right now? Draw out your two possible answers. We got, if it acts as a nucleophile, it's going to attack the most electrophilic spot. We've got two possible electrophilic spots. Okay? Attacks in. What happens? This is a good structure. No. What's wrong with it? It's got a charge. We had charge over there, and I said you were okay with it then. Why are we not okay with it here? That carbon has a lot of other oxygens attached to it. Those three electronegative groups are all going to start to really pull on that carbon, making this an unstable structure. So what happens? The electrons come back down and reform the pi bond. But then what happens to the carbon?
Too many bonds.
Too many bonds. Okay. So we have to break a bond. What bond do we break? We have to break a bond with an oxygen. Which bond to oxygen do we break?
Either or.
It is a complete and utter coin toss. Okay? How do we decide which one breaks? Well, look at the product. Okay. If it kicks out the O-ethyl, we go right back to where we started. So that was kind of boring, so I'm not going to write that one out. I'm just going to write out the one where it exchanged. And what would our other product be? Methoxide. Negative O-methyl. This is the complete epitome of an equilibrium reaction. We said both of those are equally likely to be ejected from the structure. So how do we know which side of the reaction is favored? Don't even have to go to lab. Switch this up a little bit. Maybe this will make it a little bit easier to see. So we could, that makes it less of a bad leaving group. Anybody speak French? Any famous French scientists? Le Chatelier. What does Le Chatelier say? The side of our equilibrium is going to be favored depending on all sorts of different things present. What did we do to run this reaction? We took A, our starting material, and ethoxide, and we mixed them together. How much methoxide did we add? None. Which means our initial concentration of this species, whoa, that's an eraser, that's okay, of this species is 0. Our initial concentration of this species is 0. Which way does our equilibrium favor? Towards the products. Okay. We now look at our reaction that could equally go in the reverse. What's the relative concentration of methoxide versus ethoxide? You have a lot of ethoxide and virtually no methoxide. The result is what? You exchange methoxide for ethoxide. Okay? So we change out the ester, also known as a trans-esterification reaction, which we'll talk about in more detail. It sounds really fancy, but it says esterification, meaning you make an ester. Trans, meaning you just exchanged it. You start with an ester, you end with an ester. That's all trans-esterification means. Okay? What happened on the top end? If it acted as a base, where's our acidic hydrogen? In the middle? What are you talking about? I see a carbon in the middle.
Well, there's 2 hydrogens.
Remember how I said if you don't see the hydrogens, you got to draw them all in? Draw all your freaking hydrogens in. Why are those hydrogens acidic? Why is it more stable? Resonance. We generate a resonance-stabilized intermediate. So with this choice of starting material, we've got an interesting dilemma. Okay? Number one, we have the possibility to make the enolate, which is resonance-stabilized, which means it can exist and does exist to a certain concentration that could then be active as a... What can this species now act as? Nucleophile or a base. If it acts as a base, that was pretty boring. They just went backwards. Okay, so we now have an active nucleophile. Okay, would we expect that active nucleophile to attack any of the carbonyls that are already floating around in solution? There's a lot of sterics. Okay, taking a step further, we've got resonance stabilization within our malonate ester, okay, in that enolate, that is now shuttling electrons back and forth to stabilize those carbonyls even further. So those carbonyls are not particularly active to nucleophilic attack. Can they be attacked? Absolutely. Okay? But we've got a lot of steric hindrance in this. We're probably not seeing it act as a nucleophile with another molecule like it. Okay? The end result after all of this is that more than likely our nucleophile is not shown in that red box. What is the better answer for our nucleophile under these conditions? Nope. Nope. Really subtle difference. Why is this our active nucleophile? That showed, right? What did I change? I changed the methyls to ethyls. Why?
Double trans-esterification because of double hydrogens.
No, that had nothing to do with the hydrogens. We have a massive concentration of the ethoxide. In that lower equation, what did we say was going to happen? We're going to swap all of the methoxides for ethoxides. Okay, so when we go through and run these type of reactions, the base we add, we want to act solely as a base, which means if I was going to change this reaction, what would I add? So more base would help push me to the enolate that we've got boxed in. But what if I don't want ethyl groups out there? Nope. Use methoxide. We can't stop that base/nucleophile from doing a nucleophilic attack and exchanging out and doing that trans-esterification reaction. Well, if we can't stop it, let's add a base that isn't going to change it. So ethoxide in this case is a horrible choice because we end up changing our product. We end up with the ethyl ester. But if I want the methyl ester, the base I should use should be methoxide. So now when the reaction goes through and does that stupid nucleophilic attack, instead of an ethyl down there, I have a methyl. Now what gets kicked out? Methoxide. What's the difference now between that material and my starting material?
Nothing. So what's
Absolutely nothing. It's not what's the point of that reaction. The point is I don't want a secondary reaction happening in my experiment. I want one reaction. So if I look at that base, okay, ethoxide or methoxide, it can do what? Act as a base or a nucleophile. Both are options. If I change that species to being methoxide, does it act as a nucleophile in a way that changes my reaction? It has no effect on the reaction, which means now instead of nucleophile and base being chemistry, I only have base. I don't have to worry about the nucleophilic characteristics of it. So the choice of base is critical for going through and running these reactions. Which means in the course of a reaction, if you see O minus, what's the problem with O minus? It's a base. It could potentially attack and do a transesterification reaction. Again, changing our overall results. So when you go through and run these reactions, make sure the base you're using isn't going to do secondary chemistry. Questions? Yes?
Negative charge on oxygen from
Negative charge where?
on the top, right?
Top right. Would that form a double bond and take us right back to the resonance structure that we've already got drawn? Yes.
If you bring the oxygen the metal oxygen, it will break the bond with the oxygen and the this one can go away. This bond, break this bond.
No, that carbon is not a good leaving group at that point. Because then you have a negative carbon. Negative carbon is bad. Because you don't have anything to stabilize that carbon system in there. But you don't have two double bonds. The electrons in that bond are being shared with the carbon. Okay? It is not a stable leaving group at this point. We can't force it to leave.
So I'm confused about, are we trying to use, well, I know that we're trying to use methoxide, but for the product that we wanted with methoxide.
So here's the big change. We are not trying to do anything. What we are doing is starting with this malonate structure and saying, what happens when I add base? Okay? So I'm doing a drastic change on how we've been talking about it because everybody's looking at, what am I trying to do? Let me look at the answer. You don't have the answer. You must evaluate what can possibly happen at each and every single one of these stages.
So if we would have left it using methoxide,
What would we expect it to have seen for our final product if we had used ethoxide?
we would have had ethyl at the end of each.
We would have had ethyls at the end. That is it. Okay? So what we are trying to evaluate is all possible chemistries and then realize that if we have alternative chemistries in there, we will get all sorts of crap going down on us. And that's a problem. So we want to limit that chemistry. If we want to limit that secondary pathway as a possible chemical reaction, we now need to change what?
What we're reacting.
What we're starting with. Because a simple change from ethoxide to methoxide does what to our secondary pathway? For all intents and purposes, gets rid of it. We now no longer have to worry about that as an issue. Okay? Which you should like. Less things to worry about. Okay? The lesson at the end of this is, what have we generated?
Reacting with carbon.
What type of reactivity on a carbon?
Carbon nucleophile.
We've made a carbon nucleophile. What can we do with a nucleophile? Substitution reaction. Good answer. Predict the product. You got questions, raise your... Don't get too specific with your word, Sarah, because that's going to bite you. Nucleophilic attack, and we'll get at why that just bit you. Attacks our carbon. Then what happens? Kicks out the bromine. The end result is we have added how many carbons?
2.
Which means an ethyl. Okay. Whoops, that was supposed to get rid of that box too. Ta-da! We now have that as our product. Interesting question. Let's ignore that bottom box. This showed up, so we can cross that out temporarily. What chemistry is available to that molecule? What's the acid-base chemistry? What's that?
There's still hydrogen. Yeah.
There is still a hydrogen left. What could we do? Pull that hydrogen off and do another substitution reaction. Okay? Do we want to? I don't know. It depends what you're trying to get to. Okay? But we still have that acidic hydrogen available to us. So we could still do more chemistry at that position. Okay? Why is that hydrogen acidic?
Electronegative oxygen's full.
I'm not quite sure I like the electronegative oxygen option. I mean, it's sort of true. It is resonance stabilization of the conjugate base. We can take those electrons out and do resonance with it, just like we did. Oh my gosh, how many slides back on that previous slide? Exact same chemistry. Nothing has changed. You still have a hydrogen, you still have an acid there. If you add another base, you can go ahead and do that reaction again. Does it have to be the same alkyl halide? Nope, it can be any alkyl halide we want. Okay? But let's propagate on to some more interesting chemistry. What happens if we now add acid and water? What's the most reactive thing there?
Oxygen.
Why the hydrogen? Look for the charge. H plus is a strong acid. Which are you concerned about getting splashed in your face? A strong acid or some unknown neutral compound? Strong acid is pretty dangerous. You're aware of that hazard. Deal with it first. What should that strong acid react with? I want something more general. You're getting too specific. Something basic. Electrons. Where are their electrons? Oxygens. Which oxygens? All of them. All of them are possibilities. Draw every single one of those out. I will pause. I'm serious. I actually don't want you to do that. Which oxygen is going to be the best one to react with?
Symmetrical or not?
So it is symmetrical, but is this oxygen the same as that oxygen? Or that oxygen? Okay. We've got a lot of possible options on which to react with. All of them are probably equally valid. The one that's going to be most productive for you will be that oxygen. The reason why I would pick that oxygen above any of the others is what? Has to do with the double bond. We're looking at electrons reacting. Okay? And all of those oxygens, all of them have lone pair electrons to share. So what I would argue is that's all pretty useless. It's a wash. What is the one difference about that oxygen? What else does it have associated with it? A pi bond. The electrons in the pi bond are found where? In p orbitals. The electrons found as lone pairs are found in sp2 or sp3 hybrid orbitals. Okay? Our p orbitals are higher in energy. That's going to be our most likely position to attack or put the hydrogen on. Okay? The result is that we generate a resonance structure that does what? Puts a positive charge on the carbon. Is that a good thing to do? No. So what happens? It needs electrons. Where's another source of electrons? We could try and do an oxygen next to it. Okay, that will temporarily stabilize it, but it doesn't permanently stabilize it. The best option we've got is a second oxygen molecule, an oxygen nucleophile. Okay? So water attacks. We end up with that weird tetrahedral state, which I'm not sure I've got drawn here. Dang it, I didn't draw it. So let me back off that. We'd end up with that weird frick balls. I'm not repeating that. End up ultimately at a state along these lines. Is that a stable structure? What happens? The electrons come back down, and eventually what we will kick out is the equivalent of a ethoxide. So we run through another equilibrium reaction. Whoops. Actually, I think I can advance to the next slide. Where we've got this and our other product, ethanol. Which way does our equilibrium favor? Why would it go to the right? If we have more alcohol, that's going to push us to the left.
You have more acid. You're right.
The acid's a catalyst.
Because originally you had minor reactants that pushes to the side.
Closer. We added water. There is a ton of water in this situation, which means the overall concentration of water is high on the reactant side, which does what to our equilibrium? Pushes it towards our products, and we end up kicking off the ethanol, and we're left with the diacid. It goes through and does this reaction twice. Okay? Neat, because we now have a carboxylic acid. What can carboxylic acids do? Come on now. Acid-base chemistry. Right? Turns out they can do some more stuff that's kind of interesting to us. We can add heat. What happens now? And just to be sort of nice, I'll give you a hint.
You said heat gets rid of the acid.
Protonate. Okay. Lewis acids accept electrons. Remember when we talk about acids and bases in here, we're talking about Bronsted-Lowry. So if I say acids, it's Bronsted-Lowry. If I say nucleophile or electrophile, then we can think about the Lewis acids. Okay. So if they protonate, that means hydrogen has to be picked up by something. What picks it up? What do acids react with? Characteristic of a base is that it has electrons. Does it have to be an actual base? No. Doesn't matter what it is. Something basic is going to pick up that hydrogen. Could that something be water? Yeah. There's lots of water floating around in that solution. Could it be a carbonyl oxygen from another molecule of this guy? Yep. Anything with electrons can pick it up. So what we're going to do is take those electrons and we will put them on the oxygen. What happens?
Resonance stabilization.
We could look at resonance stabilization, looking at those pi electrons, where those electrons shift in and resonate with that pi bond. Okay? But that doesn't really take us anywhere. It is valid. Okay? That's why it acts as an acid. Okay? But we need something else. And I gave you a clue. What's that clue? CO2. What's our Lewis structure for CO2? Oh, and I kind of oddly drew that sideways. That's a little bit weird. What does that kind of look like?
If you put a form of pi bond between that oxygen and carbon, then, yeah, double bond it.
And if you had 3D glasses, they'd be jumping out of the page at you. Okay, you laughed. That's good. Okay. But the problem with that is that that carbon still has too many electrons. What do you mean? Why? So what are you suggesting happens? That purple bond does what with its electrons? Goes where?
Goes down where it's
Left.
Yeah, so the carbon.
Let's go ahead and just put it there. So we now have our CO2 and we have so CO2 is great, so that's big driving for this reaction. But I now see a negatively charged carbon. Aren't negatively charged carbons incredibly unstable?
Is
Is
that
this-
negatively charged? It's not negatively charged because carbon has 4 electrons, so it's fine.
It is officially negatively charged. It just gained electrons. It absolutely gained electrons.
Okay.
Okay, so if we draw in our
I don't
bonds,
see it that way, but, oh, because it has a hydrogen. Gotcha.
okay,
So does hydrogen.
if that is incredibly unstable, this reaction does not occur.
But it's in acidic conditions, so that hydrogen,
Even if it's under acidic conditions, it's still not going to occur because we don't have the electrons until it's left. Once it's left, sure, we can put on the hydrogen, but it would have to break that bond before it could
yeah. Right.
form. Okay? So that still can't happen. Even if it's under acidic conditions, we can't protonate it right away.
Okay.
Something needs to stabilize that. What stabilizes that? What do you mean, can you do resonance stabilization?
The answer is always resonance.
Thanks, it's always been that way.
We have resonance stabilization in a situation that is very similar to the
Are you saying
keto-eno tautomerization. That is what drives this decarboxylation. If we do not have that resonance, can we form the negative carbon? No. We must have that carbonyl at that location. If it is not there, this reaction does not occur, and we're stuck. Yes?
You still have the alcohol on the other side, like that should be.
Yeah, I'm just kind of running out of space to draw it all in there. But yes, the structure continues out. What do I have, ethyl at this point? No, it's water. Sorry. The acid. Now that we've formed it, can we permanently stabilize it? With what? Our H plus, because we're looking at carboxylic
So
acids.
then you have the alcohol.
Now we're going to come back down and we end up forming not the alcohol, but the carbonyl. Remember, when you look at your tautomerization, which side is favored? We look at a ketone versus the enol. Which way does that equilibrium favor? Always the ketone. Okay? Not always, but nearly always. Neat. That last step is what's known as a decarboxylation. D for removal, carboxyl for our CO2. Yay, more practice. Now have questions for Monday. Shows up in fatty acids. Okay, so this type of a reaction is very, very common in biochemistry. Okay, that's why we look at this. If we look at the synthesis of a fatty acid, it goes through the malonic acid ester synthesis. Okay? And that's happening up in that very first step, or second step, right up here. So we can start to add carbons to a fatty acid to increase the chain length. Okay? So kind of a neat process. This isn't something that just happens in organic chemistry, it happens in biochem. Yeah, good for you. Okay? So it does show up. And I'm more than willing to go through this reaction in more detail if you would like. It did take me a little while to process it and actually figure out what's going on with it. But it's pretty much adding a carbon at a time to get you up to roughly 16 carbons, okay, for your fatty acid synthesis. And your body does this every day. Cool stuff. Okay? So the next chemistry that we'll whip through in about 5 minutes is looking at the next section, which is 23, maybe part of 24, I'm not sure exactly, which will be the last section that I'll put on the exam. So if you want to note it right now, for exam 3, what I will not ask you about is what is referenced as Gilman reagents. Okay? G-I-T. No?
What the heck?
Gilman. I said, how do you spell it?
Yeah,
Come on.
G-I-T, I'm like, yeah.
Well, I started to spell Gilman, and then realized I could get away with just IT. Gilman reagents. Yeah. You actually already know what Gilman reagents are. The malonic ester, that compound, is a Gilman reagent. So what you're not going to be responsible for is how Gilman agents react, which I believe is all of chapter 24. Okay? So I will go through and edit the homework to remove Gilman reagents from it. Okay? Other common names that will go along with that, Michael additions and Robinson annulations.
Those reactions.
You do not need to know those. Those are grouped in with Gilman. Okay? Gilman is the type of reagent. A Michael addition is using a Gilman reagent to react with a very particular starting material. A Robinson annulation is a Michael addition followed by aldol chemistry,
Which is what we do.
okay? Which is what you did in lab. Okay? So you're not responsible for those. You are going to be responsible for aldols. All right, so what's happening with an aldol? So we take an aldehyde. So we've got a starting aldehyde there, and we add what?
Base.
A base. Oh man, I didn't stepwise through this. What's that base going to do? Deprotonate. Where does it deprotonate?
Most acidic.
The most acidic hydrogen. Why is it the most acidic? Why is our hydrogen that was removed in this case the most acidic hydrogen? There's resonance stabilization. Okay? That resonance stabilization gets us to the enolate, okay, or enol, depending on what you're looking at. In this case, it's the enolate. That resonance stabilization allows this to occur. Okay? Interesting feature. If we take this aldehyde, acetaldehyde, and we add ethoxide to it, this undergoes another reaction. What's the product? Yeah, this is where this chemistry gets a bit weird, because that was actually nice. I actually drew out the enolate. Officially, what you will see is you will see this aldehyde. You'll see a single material with ethoxide takes you to this product. What is that product? As a hint, the enolate is part of this. The enolate feeds you a nucleophile. What do you need to find? Find that electrophile. Do you guys like a hint for the electrophile?
End up with a ketone.
There's your electrophile. What's the quizzical look? What's so quizzical about that electrophile? What's wrong with that electrophile?
Starting material.
It's the starting material. When you run a reaction, do you take a single molecule and react it with a single molecule? No. You're running these with billions upon trillions of molecules. Taking a step further, when we take a look at that very first step, I did a really horrible job with my arrow in that case. That very first step is actually an equilibrium step. Which way does the equilibrium favor?
The right. Oh.
It favors our starting material, which means there is a very low concentration of this guy present, which means it's most likely to run into another one of these guys, which happens to be our electrophile. The result is this guy. Okay. We took our nucleophile, whoops, no, that's okay. Our nucleophile, which we'll draw in red here, is now right here. The new bond formed is this one. It attacked the carbonyl, causing the pi bond to break open. And we end up with that product. A little bizarre. Okay. This structure most typically is in the presence of some mild enough acid that we can protonate it and we end up with this final compound-ish. This final compound is what's known as the aldol, because what functional group do we have here? An aldehyde. And what functional group do we have here? An alcohol. So we have an aldol. Okay? Yep.
I don't understand, okay, where is the electrophile attacking on our?
The electrophile never attacks.
Or the nucleophile, where is the nucleophile? Because with the bond, it's formed.
So here's our nucleophile.
Yeah, and the electrophile will be the carbon.
Attacks there.
Oh, that's.
Our electron breaks open. Yep, it's a hydrogen.
But then that's not our starting product. That's part of our starting product.
That's our nucleophile. Our electrophile is right here. Now in blue. There's our nucleophile.
Yeah, so that flips, yeah.
So hydrogens are always implied.
And so that.
There's your hydrogen.
Picks up a hydrogen from solution.
And to get to the aldol final product, it picks up a hydrogen from solution.
You
Yes.
don't have to add anything.
You don't have to add anything else.
I mean, I haven't drawn as pretty as that, but
Yeah.
it looks like it's.
These are notoriously difficult to draw, and what we drew here was the simplest version of it. Okay.
Mine looks like a monkey.
So if you've talked to tutors, okay, and if you've listened to me, we have mentioned that you should number carbons.
Yeah.
Guess where numbering carbons becomes exceedingly important? Anything to do with aldols, because it is stupidly easy to lose a carbon in this process. Okay, so number your carbons and make sure you don't lose them. We started with 4 carbons and we ended with 4 carbons. They are there. It may look all sorts of weird, but they're still there. Issue with this? What is special about that carbon that's now being circled in purple of our aldol that's not showing up?
The nitrogen.
What? Oh, I did circle it up there. What is special about that carbon? is two acidic hydrogens. We could pull one of those acidic hydrogens off and we have a negative charge. Where can we stabilize that negative charge? Resonance or an elimination. Aldol reactions will almost always complete as an aldol condensation. That was kind of fun.
That was pretty on point. That's what
It's actually kind of true. It was. Okay. So you have to watch out for this.
So
That's
if
not
you,
the final product. That's the final
Our
product.
final product is right here. The one thing I will caution you on to be careful of, make sure you answer what the question asks. If the question asked for the aldol, did I box in the correct product? No, because it's not an aldol. If they ask for what's the product, this is what you get. Okay? Secondary chemistry up the yin-yang. Okay? Kind of out of time. I want to see real quickly here.
Are there reagents or catalysts necessary to make it work?
What started this whole reaction off?
The NaCl, but we don't have
Strong base.
All you need is a strong base. Yep. There are other caveats and limitations within this. It is often followed by that secondary chemistry, either condensation or elimination. Okay, all sorts of possible things can pop up out of that. So be aware of that secondary chemistry. Pretty sure the next slide is all practice. This practice is all fair game for the exam. So everything on these slides is fair game. Okay, which I believe there's only 2 slides left. You get this practice, some aldol lessons. I'll keep Clayson off the exam. But all the aldol possibilities are valid. Okay? So there are questions. So if you've got questions,